Thank you, thank you. So this is pretty similar to similar idea, similar motivation to the previous work that you just saw from Baldi. So we present on Pico. So sounds like food and sounds like those cool collective operations libraries that we are seeing over there. So, and again, the idea is to bring them to OpenMP. So we're going to discuss a bit about the syntax and also the implementation supporting multiple devices. Oh, okay, it's fast. So the agenda is motivation. That's going to be quick because we just saw a good motivation. I'll just try to comment on the extra things on that. Then I'll show the libraries, some results that we got with our experiments, and then our conclusions. So we all know collectives are important. They appear in many AI, deep learning training applications, and HPC. Here we have some examples. In a broadcast, we copy the data from one root device to every other participant. But we also have a get operation in which you grab slices from an array on the root. We have reductions where you combine the data that is scattered around different devices and combine them using an operator. So this collective operation also has some computation in it. And the cool thing about collective operations is that they can be fast because they are going to be executed through a specialized algorithm that can be, again, be topology aware. But they also improve readability because you don't have to understand that that code is doing a reduction. You just read the name, that's a reduction, you know what it's doing, what is it for. But since we don't have collectives in OpenMP right now, we have two options. You can either use one vendor specific library and kill portability in some sense, or you can do it manually and then have a code that is more error prone and the challenge of doing it every time every program that's going to use it. And there are a few challenges that we have when implementing good collective algorithms is that you have to be aware of the latest between your devices. You have to know your topology, just like we just saw, and you have to do it in such a way that it is portable, meaning that you cannot optimize for one specific cluster and okay, call it a day, because you want that algorithm to run in different programs and different systems. And okay, I was scared because I changed the page here and didn't change there. And when we think about the interconnects of our systems, we know that HPC systems are, have this deep complex memory hierarchy. And the way our device is connected, just like we saw in the previous presentation, we have multiple links and multiple ways through which they connect. We can even have multiple PCI Express routing switches. So when you think about computation or how the devices are going to can utilize those links, it can get pretty complex. Inside one single node, so let's imagine this is one HPC node, you have the PCI connections, you can have NV links or other vendor-specific device links connecting your GPUs or other accelerators. And between nodes, we can have Ethernet connections, InfiniBand connections, those fancy, fast interconnects. But the link is not the only characteristic because usually it's not a uniform all-to-all connection inside a cluster. You can have a Dragonfly topology or a factory topology that is more common, like you have a switch that connects the nodes in one rack. And then to communicate between nodes inside the racks, you have one speed. But if you want to reach a node that is in another station, you have to hop through two switches, so your speed is different. Your contention conditions are different. So that's a challenge that we have to consider when writing collective algorithms. So talking about OpenMP support, we know that OpenMP evolved to cover this offloading model, that we have a host and an accelerator. It is generic, but let's take, for the sake of the example, the GPU case. You can use OpenMP to mark a region of code that it's going to run on your GPU, and you can say the data that's going to be moved there for the computation and the data that has to be moved back. So here's one example of Pragma targets. We are specifying that data, the whole array data, is going to copy to the device. In this case, device one, they're going to run this kernel and then move that data back to the host. And that exists right now and it works. And it's a portable way to map this kind of kernel to the accelerator. You can even run task parallelism inside a single device And as it is for now, it's supported by multiple compilers, and you can write code and run it on your AMD GPU or your NVIDIA GPU, and it should work just fine. But looking at things, some features that would be nice to have to cover those bigger systems with more accelerators is to have some sort of multi-device communication primitives, like a broadcast. But then, and also other collectives like the reduction, outward communication, and so on. But then again, that brings another syntax problem that we have to cover. That is giving an interface for the user to group devices logically. So you want to broadcast data, but you want to do it to a set of GPUs or a set of other accelerators. So we need a syntax for that, and we need to be topology aware. In this code example, we run a kernel here that modifies this array data. And here we are doing a broadcast. So for every device that we have in this variable number of devices, we are allocating memory on the accelerators and then using OMP target main copy to copy that data to each of those accelerators. One thing that we could do here is add a parallel for here and run this in parallel. But then again, this is going to be a broadcast. We are sending the same array data to everyone. So what we want to see if it's possible, if it's feasible, is to have this kind of interface, OMP target bcast, that would perform a broadcast on a set of devices. And can we extend OpenMP target model to cover those collective operations and preserve the programming model and the portability? So we try to achieve that with OMPCCL. So we implement some portable collective operations. We propose a syntax for specifying device groups, and we test some topology aware algorithms and get some speedups of up to 5 times compared to naive implementations. So let's take an overview over this library API. So as we have now implemented, we have an API interface that interacts directly with this library. We have an abstraction for device groups and the call to collective operations. And we show some ways in that they could be integrated with existing target features. It's pretty small right here, but it's the signature of the functions for the broadcast, for the scatter, reduce, and or gather, which are the ones that we implemented. We have pointers to the data, to the list of devices, the reduction operation that's similar to MPI collectives function call signatures. And a very overview of the library. OMPCCL sits on top of the OpenMP library and uses the OpenMP target routines to execute them. So if our algorithm decides that we want to move data from GPU1 to GPU2 to conclude this broadcast, that's going to happen through an OpenMP target main copy. One benefit that we get from this is usually OpenMP target routines fall back to vendor, like could device to device copies if that's available. So we remain portable. And just some comments on the implementation. We run it on a cluster with multiple nodes and multiple GPUs. And one way that our broadcast executes, so imagine we want to take this piece of data here and send it to every GPU. So here we have remote nodes running OpenMP, and here we have remote GPUs. One strategy that our algorithm does is first copying the data to the remote hosts, and then the hosts copy the data to the local GPUs instead of sending them across the whole network for each data movement operation. And that's it for the algorithm. So here's a small example of a broadcast using our proposed interface. We try to keep it similar to what OpenMP has today and be vendor agnostic. So just going through this code here, it's simpler than it looks like. So here, first line, we're getting the number of devices, then the size per device in this variable, the size of the buffer that we're going to send. Here we have a list of destined devices. That's something that we're going to use for abstraction for device groups. We first allot the memory in each device, and here we're creating a device group. That is the interface that we are proposing for grouping devices in this struct. And we pass this device group variable to the broadcast function call. So I have the host pointer, the device pointers, size per device, and the device group. And with this information, the algorithm knows how it should perform the broadcast. And here, so the API calls are implemented, and we also thought of some pragmas that could be integrated. We don't have compiler support for those, they're just a proposal. When we run our benchmarks, we are writing the function calls by hand. But let's imagine some pragmas that could integrate with the target model and keep this declarative style of OpenMP to describe the broadcast. And again, following this philosophy that the programmer describes what kind of operation it want to execute, and the runtime decides based on the topology and the data how to execute it. So again, we are creating a device group here in this variable. Here we have a enter data map to device one, and here we have a broadcast to the device group called my group. With that information, we can now here we're creating a test group and specifying that we're doing an all reduce over this variable. So with this syntax, the runtime has sufficient information to execute a reduction and then broadcast the data to all the devices in the device group. Now for some experiments, we run our experiments on the IWOMP cluster. This is our software stack. Each node has two InfiniBand interconnects and four V100 GPUs. And we are going to run those with multiple nodes. We use containers and epitainer containers for singularity, and we use it spinner for parameter sweep experiments. Spinner is a HPC benchmark tool that we developed in-house to help keep track of the artifacts. And just one quick comment. I said that we're going to use remote GPUs. As for now, the way that we have that is through the MPI proxy plugin. That's another work that's from our laboratory. That is a plugin to allow us to access remote nodes on remote devices, remote accelerators on remote nodes using an MPI communication layer. That's transparent to OpenMP. In OpenMP, you just run a target region, and let's say device 7 is a remote GPU that lies on these other hosts. This communication layer from the MPI plugin is gonna manage that. So we have two kinds of two binaries that we execute. One that goes on the host node and launches the application, and the other that launch on the worker nodes that are every other node that are only there to expose their devices as OpenMP target devices for the main application. We can talk more details about that later, but the takeaway is we can access this GPU D0 here, just like as we can access a local GPU here on the host node. So some experiments, we have this blue line that is the naive implementation, that is just a dummy for loop sending the data or grabbing the data and then distributing it after the reduction operation. And we have this other line here that is the specialized algorithm. We can see that for the reduction, we almost get an ideal weak scaling case. So let me talk about the graphs first. Here we have the number of GPUs on the horizontal axis. We go from 4 to 64 GPUs. When we are considering only 4 GPUs, that's just one node. And here we have the execution time end to end of the application. So the broadcast is the easiest one to understand because if we are sending over remote GPUs every time from the host, it takes a while to send the data there. But if we first send the data to the remote host, and then from there we propagate to the local GPUs, it can be done not only faster, but also in parallel across the hosts that already have a copy of the data. And the other experiments here. Here we have two more experiments. Okay, so here we are running those collective algorithms. These two graphs are 64 GPUs, and we are changing the size of the data that we are operating on. And we can see that for small input sizes, it's more or less the same. But as we get larger and larger buffers, a gap appears, and we can see the benefits of using our specialized algorithm. So here on the vertical axis, we have the throughput. One cool thing that we can observe here is that the blue line, the naive implementation, saturates around the theoretical throughput of our InfiniBand links on the node. While when we have a specialized collective algorithm running, we can leverage those parallel links and the topology of the system and achieve a higher throughput. So, summary for work. We present on Pico, that's a portable multi-device collectives for OpenMP. We have a nice speedup, again, comparing against a naive implementation, but we propose an interface that tries to be compliant with current OpenMP model. A natural continuation of that is to consider asynchronous collectives, present pragmas that are more integrated with the target model. As for now, we don't have front-end compiler support. Every experiment, we wrote the API calls by hand. And also, we want to study more how we can get portable topology information. So we can just run the binary and the algorithms have an idea of how to execute efficiently. And that's it. Thank you.
So, questions? I'm sure there's a question or some thought. So you can imagine going through the MPI spec and looking for all sorts of other similar kind of operations and implementing those as a way to make your thing richer. And then the other thought is the PGAS people like EPCC and stuff have had to do the same exercise of sort of collective communications. I think it was thinking NPI, right? So that might be also a good prior art to look at. So I think this is great work.
Thank you. That makes sense. One thing that we saw in NPI MPH implementation specifically is that how they change the algorithm based on the size of the buffer. So if your buffer is bigger than a certain size, it switches to a binomial tree propagation, then a binary tree, and there are a lot of algorithms there. But I think PGAS is a good place to look at. I'll check that, the rationale, because it's different from this memory model that we use in NPI.
Okay, we have time for more questions.
Maybe this is more to do with MPP. You said it recognizes GPUs on a different host, attached to a different host. How does the numbering or how does is it completely transparent to the user?
Yes. So this is a work that was published by Jonathan. That's the first author of this work in Europar this year. And what we did was extend the LLVM implementation of OpenMP that has this list of devices that it detects when you launch it. So there is this agnostic layer and the plugins layers. And we created the MPI plugin just like as another plugin that launches and attaches to this agnostic layer. So when that implementation starts up, it just uses this as one of the plugins, and it loads up plugins on the remote worker nodes. But even for the runtime execution, the OpenMP runtime running, it just sees it as the other devices. So it supports all the other functions: OpenMP main copy, OpenMP the kernel launch, and so on. As far as OpenMP code goes, it's just a target region that goes to a remote GPU.
Okay, so the device group will create a group of these devices, and then this will just create communicate to all the GPUs on those devices.
If you create a group, yes, but our implementation of device group is not complete. So that's a separated work. On the MPI proxy plugin side, it just appears as a flat list of devices. If you are to create a topology of a group, you can group those, let's say D0 to D3 in a group because they are local to each other. But from OpenMP code perspective, on the MPI proxy plugin, they are just a list of devices, GPU 0 to GPU 63. And you may happen to know that GPU 63 is far away and GPU 0 is local to your PCIe bus. But that's something that we think on exploring in the future. Because as it is for now, our collective algorithms do consider the topology, but from the OpenMP side, it's just another device that happens to be remote.
You have time for one more.
Yes, go for it.
Slide 15.
I don't think the next presenter is gonna mind.
Yeah. I'll speak to
How many
him.
GPUs are you using here?
What, sorry, which GPUs?
How many GPUs?
64. And on the other one, this is a 1 gigabyte buffer for every case, around the number of GPUs. And here we fix the number of GPUs in 64.
You happy now? All right, I have a question about your MPI blocking too. So I know that there used to be a Google RPC based remote offload blocking that would load off my network. Do you have any plans to upstream that and contribute it to the LVM project as like
Yes.
an option?
Yes, we do. Actually, that's something that we are really, I don't know if eager is the word, but we very much like to merge it. And that's one change that we did to make it mergeable, because in our first implementation, it was a single binary. And upon launch, based on the rank, it would pick one to be the host node and the other ones to detect the devices. But for it to fit the fat binary specifications, we separated it into binaries that are generated upon compilation. And there's an open pull request on the LLVM GitHub for this MPI proxy plugin,
Okay,
and it's under revision.